There is a tool called truffleHog. It scans Git repositories, every commit, every branch, every tag in the history, looking for strings that match the patterns of known secrets. API keys, private keys, tokens, passwords. It runs against a repository of moderate size in under a minute. It is free. It requires no special access. Any repository that is publicly visible on the internet can be scanned by anyone at any time without the owner knowing. This is not an advanced attack. It does not require knowledge of the target organization, their systems, or their technology stack. It requires a repository URL and 30 seconds. The reason this works so consistently is not that developers are careless. It is that the Git data model was not designed with secret detection in mind, and the workflows that developers use every day make it very easy to commit a secret accidentally and surprisingly difficult to remove it completely. Git records every change to every file in a repository, permanently, in a structure that is designed to be distributed and replicated. When a secret is committed to a file and then later removed, the removal does not erase the original commit. It adds a new commit that changes the file. The history of both commits remains in the repository, accessible to anyone who clones it. That is not a bug. That is the core property of version control that makes it useful. But it means that a secret committed for 5 minutes and then removed 5 years ago is still in the repository today, in the commit where it appeared, reachable by anyone who knows to look. Most developers understand this in principle. The operational reality is different from the principle in one important way. The pace at which code is written does not leave room for auditing every commit before it lands. A developer who accidentally commits a .env file notices immediately, deletes it, and pushes the deletion has done exactly what felt like the right remediation. The secret is gone from the current state of the repository. It is not gone from the repository. Public repositories are the most obvious exposure surface, but they are not the only one. Private repositories that were made public briefly, during an open source evaluation, during a migration between hosting providers, during an accidental misconfiguration of repository visibility, were indexed by search engines and automated scanners during that window. The indexing happened faster than the visibility change was noticed and corrected. The window may have been minutes. The indexed content persists in caches and search results indefinitely. GitHub specifically maintains a search index that covers public repository content. Automated tools scan that index continuously, looking for patterns that match known secret formats. AWS access keys follow a specific pattern. A 20-character string beginning with AKA. Stripe API keys begin with SK Live. Slack tokens begin with XOXB or XOXP. Google Service Account credentials appear in a specific JSON structure. Each of those patterns has been codified into scanning tools that run against the full index of public GitHub content around the clock. A secret that is public for long enough to be indexed, which in practice means any secret that is committed to a public repository and not caught within minutes, has been seen by automated systems and may have already been acted upon. The economics of this matter. An attacker scanning for exposed secrets is not targeting any specific organization. They are running automated tools against a broad surface, collecting valid credentials, and using them later. The cost of the scanning is effectively zero. The yield, the number of valid credentials found per hour of scanning, is consistently high enough that it is a standard part of how attackers build access to cloud environments, SaaS platforms, and internal systems. The 2019 Capital One breach, the 2022 GitHub OAuth token incident, and dozens of less publicized cloud environment compromises each traced back to credentials found in repositories. The technique is not novel. It remains effective because the rate of accidental secret commits across the development community is high enough to provide a continuous stream of fresh credentials. Organization internal repositories are not immune. An employee who clones an internal repository to a personal machine, where it gets backed up to a personal cloud storage service, has moved the repository and every secret in its history outside the organization perimeter. A repository migrated from one hosting platform to another may have been briefly public during the migration. A developer who creates a public fork to test something, then deletes the fork, may not have deleted it before it was cloned by an automated archiving service. The practical model for Git secret exposure is not, was this ever committed to a public repository? It is, Has this ever been committed to any repository? And can the full history of that repository be guaranteed to have remained under controlled access since the moment the commit was made? For most repositories in most organizations, that guarantee cannot be made with confidence. The response that actually addresses the risk has two parts. Detection, running secret scanning against the full repository history, not just the current state, to establish what has been committed, and rotation of every secret found, regardless of when it was committed or how briefly it was present. Not because the secret is definitely in an attacker database, because the cost of rotating a credential is low, and the cost of not rotating one that has been seen is potentially total. Deletion is not remediation. Discovery followed by rotation is.